Good afternoon, everyone. So yeah, I'm John, and I'm the Accuracy Team Lead at Speechmatics. Our store is just over there. That's where the clapping's from. Thank you very much. So Speechmatics, we provide the most inclusive automatic speech recognition on the market, and we sell it to other businesses to build their services on top of. Now, we've also got our real-time transcription coming through on the slides here, so you can see the accuracy for yourself. So today we're going to be talking about word error rate and how actually as a metric used to look at the quality of automatic speech recognition, it's actually becoming obsolete. Now, word error rate is actually very misaligned often with what we care about as developers and also consumers of ASR. And even so, multi-million-dollar deals can often hinge on very, very small differences in this metric. And that's not ideal because if you're making, big decisions on which company you want to go for, the metric better well align with what you care about and what your intuition is. So at Speechmatics, we've been working on a new novel metric which aims to fix some of the problems with word error rate. And one that truly understands the meaning in our transcripts by harnessing the power of large language models. So without further ado, we're going to go straight into talking about what word error rate actually is and some of the problems. So word error rate is the primary metric used in automatic speech recognition, or ASR. This is just speech to text. It's been used since the 80s, since the dawn of speech recognition. And the reason it's so kind of heavily used is because it's very easy to calculate. So the first thing you do to calculate this metric is you take your reference transcript, that transcript that's actually been typed up by someone who's listening to the audio, and you align it with the one that is the output of your ASR system. And once you've got that alignment, you can start to count up the errors. And there's three types. There's substitutions, insertions, and deletions. And to calculate it, you basically just take the proportion of the total number of errors there, and you divide it through by the number of words in the reference. So very easy to calculate. And you're doing very well if you've got no errors, and then the word error rate is going to be 0. Just need to get the right slide. Okay. So actually, now let's talk about the downfalls of this metric. So first of all, in order to get that quality alignment that I was talking about earlier, you have to turn all of the text into lowercase, and you have to remove all punctuation. Now, this isn't hugely ideal because those bits of information are really important for readability. So an ideal metric would actually take that into account. There's also an intrinsic flaw in error rate. And that means that if we're driving towards a 0% word error rate, if there's any kind of errors from those human transcribers that have sat down and written it up, we can't do that. And also, they might have written down the transcript in a very different specification than what we have in the system. And what I mean by that is, say you have currencies or dates, you can actually write the same thing you say in many, many different ways. And if you choose the wrong specification in your reference transcript, you're going to be penalized by word error rates a lot. So this is all just basically to say word error rate is not very smart at all. A small spelling mistake in an unusual name gives a full substitution error, which isn't ideal when you compare it to more serious issues. So let's have a look at these examples here. So top right, the reference is, I'm a 5-year-old kid. And the ASR outputs, I am a 5-year-old kid. Now you can see the specification for that kind of written form of 5-year-old is different. And we also have the difference of I'm and I am. Now what this leads to is 5 errors. So we have 2 substitution errors and 3 insertion errors. And when you calculate the word error rate for that, it's 125%, which is kind of crazy because there's not really a huge amount wrong with that, right? And then we look in the bottom right. So we have this. We have the reference, I have sent a message, but we've said in our ASR output, I haven't sent a message. There's only one error here, so we get a word error rate of 20%. But this is a much, much more serious issue because it's actually caused misinformation about the fact that you haven't sent that message. So now let's talk about an alternative model that we can use as a quality metric for speech recognition. So there's something called the NER model, and this is not to get confused with named entity recognition. It's quite different. And this is a weighted evaluation of errors by a penalty based on the severity of error. So to calculate this, someone who's looking through the transcripts of speech recognition, every time that they see an error and they're trying to correct it, they're going to look at that and they're going to class the severity, and it can be in minor, standard, or serious. And we're going to look at some examples of those on the next slide. This is also very easy to calculate. You just sum up the addition and the recognition error penalties, and you divide that through by the number of words. But this is great because now, this captures the loss of meaning, and it much more closely aligns with what humans care about in their quality metric. But unfortunately, this is very expensive to calculate because you need a human in the loop. You need every single error, they need to decide what the severity is. So let's look at some examples. So a minor error. I don't believe executives should be able to overturn a decision. So there's just one substitution error here, and for in. And you can read easily through that. So that's why it's a minor error. Then we have a standard one. This is my sister who works at the hospital. But what it should have been was, this is my sister who works at the hospital. So there was a bit of a mix-up in punctuation there. That kind of changes the meaning a bit. And it disrupts your flow while reading it. Then we have a serious error. We omit the word suspected before murderer. This is a big deal because if you imagine this is a transcription of a court case, if you make this kind of mistake, that's not good. We're going to take a bit of a side now. We're going to come back to the NER model in a bit. But we're going to talk about large language models. So a language model is simply a model which is trained on lots of text. It takes in a context of words before it, and it's trained to predict the next word. And you see this all the time. Like every time you kind of text someone and you have 3 options for a word to choose, you're using a language model there. And this is all the rage in the community at the moment. Everyone is scaling these things to be really, really big. And they're doing that by throwing more GPUs and compute at it. They're throwing more data at it, and they're scaling the parameters. And we can see on the right here, we have a graph, and you can see that the number of parameters, which is on the y-axis, is exponentially growing. So you can see that back in February in 2019, OpenAI released GPT-2. That had 1.5 billion parameters. And then kind of mid-2020, they brought out GPT-3, which has 175 billion parameters. And even more recently, Google released Palm, which has 540 billion parameters. So these things just aren't slowing down. And the big reason that these companies are scaling language models is because there's new, incredible few-shot learning performance that emerges when you do so. And this is across hundreds and hundreds of different NLP tasks that it gets very, very good at. There's a bit of a delay on this. Okay, so let's put this into perspective here. So this is looking at Google's Palm model, and this is an example that is question and answering. And it's something that completely kind of blew my mind when I saw the power of it. So let's look at this. So the input to the language model is, Michael is at that really famous museum in France, looking at its most famous painting. However, the artist who made this painting just makes Michael think of his favorite cartoon character from his childhood. What was the country of origin of the thing that the cartoon character usually holds in his hand? And now, one word at a time, the model outputs this. The most famous painting in the Louvre is the Mona Lisa. The artist who made the Mona Lisa is Leonardo da Vinci. Leonardo da Vinci is also the name of the main character in the cartoon Teenage Mutant Ninja Turtles. Leonardo da Vinci is from Italy. The thing that Leonardo da Vinci usually holds in his hand is a katana. The country of origin of the katana is Japan. The answer is Japan. Now, I think this is really, really astonishing because all of these things are really, really unrelated. And they're things that are, very deeply rooted in our culture. And this language model understands how they fit together and how it relates to the question. And this is exactly what you get with scale. And that's why everyone's doing it. This is another one of my kind of favorite figures from the paper as well. So this is looking at 150 different NLP tasks from the big bench frameworks. And this is kind of a 5-shot system versus humans, okay? So that means that for each of these tasks, the language model gets to see 5 examples in its prompt. So we can see here on the left, these blue kind of bars there, they're above 0, which means that Palm is better than humans at these tasks. And an example is reading comprehension. And on the right, we have the ones that do worse. An example is movie recommendations. And as these things have been scaling, more and more of these tasks are going blue. They're becoming better than humans. Let's move on now to another model which Google released, I think at the end of June, called Minerva. Now, this system is really cool because it can solve high school maths problems. And the thing which I find really cool is, so they have a new state-of-the-art result on this data set. It's called the math data set. And they get about 50% accuracy. And the previous state-of-the-art was only 7%. And that's something that ML forecasters didn't expect to happen in the next couple of years. So this was a big result when it came out. And you can see here, this is what it does. So it's taking in a question about a particle that has the position vector, and it's told to find the speed. And you can see it knows how to differentiate this thing. It gives you its reasoning, and it comes out with the speed of 3/4. So how does this work? So it's taken the Palm model, and we've given it just under 120 gigabytes of more sources that have LaTeX code in there. So these are from things like archive papers and web blogs. And we also have 4 examples that we give it, so that it's still using few-shot learning. And the key thing here that I want to draw your attention to is they use chain of thought prompting. Now what this means is, in the prompt, so we've got this kind of first expression with the problem here, and then we actually take it through the working and the solution. So let's actually have a look at this. So on the left here, we have standard prompting, and this is about how many tennis balls that Roger has. And you can see that in the answer there, it just says straight off, the answer is 11. But on the right, when we introduce chain of thought reasoning, we say that Roger started with 5 balls, 2 cans of 3 tennis balls, and each is 6 tennis balls. And then it goes to the answer of 11. And then when it goes to the question that we actually care about, which is how many apples there are in a cafeteria here, it actually gets it right because it's gone through, again, its chain of thought reasoning, which is kind of highlighted in green here at the bottom. So it helps the model just understand what's going on. Okay, so we have now all of the building blocks to put together to automate that NER model that we came to at the start. And if you remember, the NER model was a way of weighting those errors, and it was much better at what error rate. So we have large language models now. We have few-shot learning, we have chain of thought reasoning, and we're going to join all of those together to get a more meaningful metric. So here we go. Okay, so this is the really kind of cool bit because it's bringing everything together. This is OpenAI's kind of playground for GPT-3. And what we've got here is 2 examples that we're feeding it in the prompt. So the first one, in the reference, it says this has been confirmed by the Pentagon, and the recognized output is this hasn't been confirmed by a Pentagon. And the chain of thought reasoning, which is underlined in kind of dark blue here, is the word has is reversed, which causes misinformation about the message. Therefore, the error is likely serious. And we do the same for that same executive one that we saw earlier, where we've just swapped in and an, and that error is minor. And now we're coming to that omission of suspected before murderer, and this is the one that we want to see what Palm is going to predict, or GPT-3 in this case. So the very final thing in the prompt is result : and then we let the language model, one word at a time, predict what it thinks is coming next. And this is what it outputs, and it's highlighted in green here. So it says, the word suspected has been omitted, which changes the meaning of the message. Therefore, the error is likely serious. So it's got it right. It's taken its world knowledge about how language is structured. It's taken the information from the two examples before it, and it does a very good job and aligns with our intuition. So let's look at these two same examples that we had last time now that we're using the NER model. So do you remember that I'm a 5-year-old kid example? That's only really one minor error because of the difference between I'm and I am. There isn't really a problem with the 5-year-old kid output. So therefore, one minor error, that has a penalty of 0.25. So we get an NER of 6.25. And with the other one, that's one serious error because it's caused misinformation, and that gives an NER of 20%. So that much more closely aligns with what we think the quality metric should be. So we've ended up with a more meaningful error rate now, which we can use. It encodes the subjective preferences on the stylistic output, and we've automated it with large language models. Still early days with this research, so how do we deal with multiple errors? Does it correlate with word error rate? And is the problem kind of just too subjective? So these are some of the things which we're working through now. So that's it for the talk. Thank you very much for coming. I hope you enjoyed it and took something away. Please come and say hi at our Speechmatics stall. Everyone give a wave. We're literally just behind the stage here. And we'd love to show you the demos which we have. And you can scan this QR code as well to try out and have 4 hours free a month. So thank you very much for listening, and have a good rest of your conference.